calculator's like, what the hell are you trying to do here? Killing me. Gotta make you. Someone programmed you for our use, right? Okay, so now I get 2.524 times 10 to the minus 4. So it should come out smaller, right? Whereas that one is 0.16. Then I multiply that by lambda, and lambda doesn't change, right? It's still 10, or it's still 10, right? So then you're gonna have multiply this by 10 divided by 4 pi. Then change it to a log scale. Woo. $83.0 decibels. Oh, let's see. Huge difference, right? There is over 111, and here's 83. Yeah, again, about 30 decibels less, right? Something like that. Okay, now how about if we make it non-uniform power distribution? So that means I'm going to make lambda some function of x, right? So lambda is equal to alpha x squared, let's say. So what would that mean physically, right? When x is 0, lambda is 0. So that would mean the middle portion of the speaker is almost no loudness at all. And as you're going to the one end and the other end, these two ends are the loudest. So what would someone hear over there? Should it be louder, or should it be... So in other words, you are now sitting in a concert hall where two sides are loud, the middle is, but you're over here. I think it should be louder because at least you're close to this end.
That's right.
Right? So it should be slightly louder. Okay? So now the only difference, couple of things we need to do is that here you need to calculate what the constant alpha has to be. So then the equation lambda is equal to dp dx. Then I'm going to have to put the lambda function, integrate this, and then this one I'm going to integrate 0 to 3 and double it. Because the distribution of the power is uniform here. It's uniformly distributed, right? So then you're going to have here 2, 0 to 3 alpha x squared, and then double, and that's going to give me the total power of the speaker, right? So 2 alpha, and then the power of the speaker is going to be 60 watts. And then this is going to be what? X cubed over 3, right? 0 to 3. So it's going to be 2 alpha, 3 cubed over 3, which is going to be 9, right? So alpha is 60 over 18. In other words, what we found is what constant this needs to be to tweak it so that the total power of the speaker comes out to be 60 if it has this distribution function. Then we take that and we set up our integral again. I is equal to dp over 4 pi r squared integral, right? Then you have here dp is equal to lambda dx. And then the r squared is the same function. And then depending on whether there's absorption or no absorption, right? So So then we put lambda is equal to alpha x squared. Right? So now alpha and 4 pi can come out, these two. But we already know what the alpha is, which is 60 over 18. So that's the number that we put here. 60 over 18 for the alpha. Now the integral becomes x squared dx over 5 minus x squared plus 16. Negative 3 to 3. Right? This one is in case there's no absorption. Right? So then you do this integral, multiply by this, and that gives you the intensity. Then you change it to a log scale. Right? So now, what if there is absorption? Well, the only thing that changes is then you put the e to the minus the 1.2, so you do this thing. Square root of, and then you still have an x squared. See? So it's the difference is that you're just adding an x squared here. That's the major difference. And then instead of 10 here for lambda, you're calculating what the alpha is, and then you're putting the alpha here instead of the lambda, right? So you're adding an x squared. So let's do the absorption one. And if you could do the absorption, then you could do the non-absorption. Okay? So since the integral is already in my calculator, I'm lazy. I'll just go and I'll just change it. Okay, so then I'll just add an extra x squared. Says busy, made my life miserable, right? So now this number comes out bigger because there's an x squared there. So instead of 2.5, it comes out 1.2477 times 10 to the minus 3 instead of 10 to the minus 4, right? But then instead of the 10 here, what do I have? 60 over 18. See? So instead of 10, we have that. So is the number going to come out larger? 60 over 18 is less than 10, right? Before I had 10. Well, let's calculate it. Multiply it by 60 divided by 18 divided by 4 pi. So the intensity comes out 3.3097 times 10 to the minus 4. Now change that to a log scale. Take the log. Right? Nice, nice, nice. A little bit louder, right? This was the absorption one, but this is the non-uniform where it's louder at the end. Well, if you're sitting at that end, you're closer to the louder end. See? How about a speaker like this? Circular. Okay? Then you are I'm going to take a bunch of rings and integrate over the rings, right? So if there's a circular speaker, then I'm over here, right? I get a ring, right? And then I am equidistant from that ring, right? So this is X, this is R. So what's the intensity that's created by one of those rings? Di is equal to dP over what? 4 pi times this distance squared. I'm going to call this one B right now, because this one I'm calling little r, right? So 4 pi D squared. So I'm getting the ring of the speaker. I'm saying my distance to the ring is D. And then the intensity is D squared, right? And if there's absorption, then I'm doing e to the minus, let's say 1.2 D. Right? Then what I'm gonna do, I'm gonna define the surface power density. Sigma is equal to dP dA. Right? Same thing that you do for voltages again, right? Surface charge density, we call it. And then dP is equal to what? Sigma times what? dA. And then what's dA? If the radius is r, 2 pi r dr. Right? Sigma dA is 2 pi r dr. So you're taking the circumference of this circle and you're multiplying it by the thickness. So that's dP, right? So now what's the relationship between the D and the R and the X? The X is the distance from here to the point, and then this is R. Well, as I go to further and further outward circles, the R is getting bigger, right? The radius of the ring. But the X is not changing, right? So then the D squared is going to be X squared plus R squared, right? So then you're just going to have here DI. 2 pi cancels this, you get what? Sigma over 2. Then you have here R dr over D squared is equal to what? X squared plus R squared. E to the minus 1.2, and then D is equal to what? Square root of X squared. Square root of X squared plus R squared. Then you're going to integrate this. I did the uniform surface power density, right? Uniform, so that's it, means uniform is surface power density. If it's non-uniform, then the sigma, you put it in there and then you integrate that, you see. So I took the sigma out of the integral. So now can I integrate that? Yeah, I integrate that, so let's give some numbers. Let's say the radius of the plate is 5 meters, and let's say the distance x is 8 meters. Right, so then you integrate that from 0 to 5 meters radius. Then the x is going to be 8, right? It kind of looks like this integral. Slightly, you don't have a 5 minus x. You just have 8 squared plus r squared. Then you have, instead of x squared, you have an x. See? This one you have to have a r dr because that gives you the area of that ring. Right? Because the further out the ring is, it has a bigger area and therefore a bigger loudness. You see? So then you go from 0 to 5. Okay, so then I'm going to go back to my integral that I had earlier and just tweak it, because I'm lazy, you know. Helps to be. I'm going to go from x dx. And here I'm going to do x squared plus 64 Then I'm going to go 0 to 5. It's the negative 3 to 3.
Oh,
Okay. Integrate that. Right. That's just the integral. Then what do I multiply that by? The sigma over the 2. Well, what's sigma? If it's a uniform surface power density, right? I have to have the half. If it's uniform, then it's just the power over the total area, right? So then it's going to be 60 watts, let's say, divided by what's the total area? 5 times 5 squared. If it's linear, it's power over the length. If it's surface, power over the area, right? So then multiply this by okay, so the total answer comes out 2.08 times 10 to the minus 6. Then we can convert that to decibels. .2 decibels. Nice. Woo. And if there was no absorption, then you would just not have this portion. Good, so with that, now the last segment is left, which will take us the first half of Monday. There'll be the Doppler effect and the cone. If you go faster than the speed of sound, then the sonic boom that you create. So there'll be the beginning portion. Probably it's not gonna take us too long, maybe 30 minutes, but study up on that too, because all that's on the test on Wednesday. So this stuff, including that, study up on it, be ahead. And then after that, I'll start Monday on the interference of waves, standing waves and interference of waves. Okay, good. Good topic here. Review all this stuff.